And finally, here is an example from physics. You know the pendulum, right? Well, the tip of a pendulum moves under gravity. What do we mean by that? Well, if I have a pendulum, if I have a pole with a string and a mass attached to it, then this gravity will pull the little mass down and will make the pendulum move. Okay, so what we want to do is you want to find out if we have this mass m, how is that going to affect the angle? So in other words, how is the angle going to change in time under the effect that gravity has on the mass itself? Well, I'm going to lead you here through some geometrical and physical considerations that will allow us to construct a differential equation. Once again, we're not going to solve the differential equation, we're just going to set it up. So let's see, what is the only thing that is working on this mass? Is gravity. And of course, gravity is going to apply a force equal to mass times acceleration, or mg. Part of that force is going to be in the direction of the string, and so it's basically going to be counteracted by the string and will be lost. So all we have to worry about is the remaining component, the perpendicular component. More shades of linear algebra here, right? So what we're looking at, and the part of the component of the force that is actually going to generate movement, is only this Ft, which is going to be tangential to the direction of movement. All right, now notice that the angle theta that the string makes with the pole at any time is going to be exactly equal to the angle theta that you see at the bottom of that picture there, because it's formed by parallel lines. Okay, so we can use this to set up some equations, some inequalities. First of all, we can tell that the force, and here I'm being a bit sloppy since we're doing linear algebra, I should say the magnitude of that force, but that's what we're looking at, is going to be mg, which is the magnitude of the acceleration of gravity, times the sine of theta, because of course Ft is on the opposite side. On the other hand, Ft, thanks to our good old friend Isaac Newton, is mass times acceleration tangentially, right? So what we're going to look at is the acceleration that's going to happen in the direction of the force, okay? And that's going to be m times, being an acceleration, is the second derivative of, or the second rate of change of the length of that arc along which the mass is going to move. Acceleration, second derivative, right? Except that we're going to compute this along the arc of the circle that is formed there. Now, how do we compute the length of the arc of a circle? Well, again, from basic geometry, that's equal to the radius, which is the length of our string L, times the angle theta, in radians, of course. We always work in radians. But L is constant, so it doesn't really come into the second derivative. Therefore, we can say that this tangential force is going to be equal to m times L times just the second derivative of theta. Okay? Now, what we can do is we can set these two expressions equal to each other. So minus mg sine theta is going to be equal to ml theta double prime. Cancel the m's that we don't need, rearrange a few things, and we come up with this equation. Well, that's a differential equation, right? It's an equation. It involves a derivative, namely the second derivative, so it's a second order differential equation. It only has one independent variable, namely, can you guess? Time. Everything is working in time here. G and L are constant, and therefore we have all the ingredients in place. It's an ordinary differential equation. Okay? The question once again is, what is the function theta as a function of t? So can we predict at any time t during the movement of this pendulum how big the angle is? Of course, once we have that one, we can figure out all kinds of other informations, data, and properties of a pendulum. So these are just three basic examples of situations where we can easily come up with a differential equation. Now the difficult part will be to solve it, to get to what we really want, and that is find out what the function whose derivatives we're playing with is all about.